critical angles, and in total internal reflection, 2D and 3D wavefronts, diffraction. So there were very important definition or concept to remember. The first thing is that you need to remember that the speed of light in vacuum is c equals to 10 times 10 to the power 8 meters per second. And then refraction of light is the change in direction of light ray due to the change in speed when light travels from one media into the other one of different optical density. We have also looked at optical density. We've said optical density will be a measure of refracting power of a medium. That is, the higher the optical density, the more light will be refracted or be slowed down as it moves through the medium. So we have said that refractive index represented by the letter N of a material is a speed of light in vacuum, is a ratio of speed of light in vacuum to the speed of light in a material. That is N equals to C over V. So it's the more, the denser the material, it means the more the V, that is the V, which is the speed of light. The more denser the material, the lesser will be the V. So meaning that if we are dividing C with a smaller number, you'll be getting higher value of N. So meaning that if you are having a denser material, light will travel more slower, and then you'll have high refractive index. Right. And we have also discussed the normal. We have said the normal is a line that is drawn perpendicular to the plane of surface. So you can see if we are having the plane of surface here, this will be the normal that is drawn at the right angle to the surface. And then the angle of incidence will be the angle between the normal to the surface and the incident ray. And then angle of refraction will be the angle between the normal to the surface and the refracted ray. So this is the angle of incident. This is the angle of refraction here. Right, Snell's law. Snell's law is states as follows. The ratio of the sine of angle of incident in one media to the sine of angle of refraction in the other medium is constant. So that's what you need to know. So here you can see that the ratio of sine of angle of incident in one media to the sine of angle of refraction in the other medium is constant. So these two will always be this will always be equals to this because they are constant. Right, it can be expressed as follows or be written as follows. So 1 subscript 1, they mean angle of incident, or it means a refractive index of the first material, the refractive index of the first material. So it can also be written as follows. Right, so we have said that the refractive index can be calculated as sine of angle of incident over sine of angle of refraction. Right, so it can be this, the refractive index will be the sine of angle of incident over the sine of refraction. So, and it can be used to determine the refractive index. This equation can be used to determine the refractive index of an optical medium for a ray light traveling through the from vacuum or from air to the medium. Right, let's look at law of refraction. So law of refraction is that the angle of incident will be equal to the angle of refraction. When light is refracted, the angle of incident is always equal to the angle of reflection, sorry. Right, so now angle of reflection is the angle between the normal and the reflecting surface that reflected the ray. So like if you are having this as a reflecting surface, the angle of reflection is the angle between the normal to the reflecting surface and the reflected ray. So it will be, angle of reflection will be the angle between the normal to the reflecting surface, that is the line that is drawn perpendicular to the reflecting surface, and it will be between the normal to the reflecting surface and the reflected ray. Right, I is the angle of incident and R is angle of refraction. Right, remember that we have talked about critical angle and total internal reflection. We have said total internal reflection occurs when refracted ray does not emerge from the media, but it is reflected back into the media. So there are conditions for total internal reflection to occur. The first thing that you need to consider is that the light must be traveling from an optically denser medium, a medium of higher refractive index, to an optically less dense medium, a medium of lower refractive index. And then the angle of incidence in an optically denser medium must be greater than the critical angle. Now, what is the critical angle? The critical angle is the angle of incidence in an optically denser medium for which the angle of refraction in the optically less medium is 90 degrees. So now, for total reflection to occur, light must be traveling from an optically denser medium to an optically less denser medium. Now, as you can see, this blue light here, it has undergone total internal reflection. It has been reflected back into water, where light was traveling from an optically denser medium. Hello?
Some of the learners are asking that you just slow down a little bit. They're saying that you're very fast.
Okay.
Not a problem.
Refraction will be 90 degrees. The angle of refraction will be 90 degrees. So you can see that if this side is 90 degrees, it means also this side is 90 degrees. So the critical angle is the angle of incidence in an optically denser medium for which the angle of refraction in an optically lesser medium is 90 degrees. So if it's 90 degrees this side, it means it should be 90 degrees. So now remember that we have said two things. We're about the total conditions for total internal refraction to occur. The first thing that you need to remember is that total internal reflection is when light does not go through from a optically denser medium, is reflected back to the the medium, like the blue light here. So two conditions must be met for that to take place. First thing is that a angle of incidence must be greater than the critical angle. So if we look at the blue light here, you can see that the angle of incidence, which will be this angle over here, is greater than this one in red because it is from the normal to there to the blue light. So it's greater than the one in red. So it's greater than the critical angle, meaning that if it's greater than the critical angle, then total internal reflection will occur. But what is the second condition? The second condition is that light must be traveling from an optically denser medium to an optically less denser medium. So glass is optically denser than air. So that is why total internal reflection is occurring. Right, you can see that you are having air here, which is having optical density of 1, and your glass is having optical density of 1.5. Right, let's carry on. All right, we have talked about the critical angle. So we have also talked about the application of total internal reflection. Sorry about that. I had a problem with my screen. It was not moving. So we have said that total internal reflection, it is being used in medicine. So in here we have said it can be used in endoscope and in gastroscopy. That is imaging of the stomach and other imaging that would have not been possible without surgery. So now instead of using surgery to view certain organs or certain parts of the body, you can use endoscopes. So now also there are industrial endoscope, which are fiberscope and boroscope. These ones are used to image the interior of machinery without having to dismantle big machinery. You are able to view the interior of the machinery. Right. And also it is used in spectroscopy. So here we're talking about analysis of substance that is unable to be placed inside the spectrometer. So instead of having to destroy your sample or making it smaller to fit there, you just view it from the outside using optical fiber bundles. Right. So you are able to know exactly what is the composition of that particular material. We're looking at 2D and 3D wavefronts. So which is what we'll be spending our time on in terms of the assessment today. So a wavefront is an imaginary, this will be an imaginary line in that it will be an imaginary line that is in an imaginary line joining the points on a wave that are in phase. So we also have Huygens principle, which said that every point on the wave front serves as a source of spherical secondary wave that move forward in the same speed as the wave. So here we are saying a wave front is an imaginary line joining points on a wave that are in phase. So, and then we are saying Huygens principle states as follows: every point on a wave front serves as a point source of spherical secondary waves that move forward in the same speed as the wave. So if we are having a wave, you will be having it will be an imaginary line that joins the in phase and points that are out of phase in grade 10. Now, Huygens principle says every point on the wave front will be serving as a point source of spherical secondary wave that move forward with the same speed as the wave. Now, we come to the concept diffraction. Let's look at the concepts that we have defined so far. We have defined reflection, which is the bouncing back of a wave. And then we have also defined diffraction, refraction before diffraction. And we have said that refraction, it is the bending of wave as it moves from a medium of different optical density. It is the bending of wave. Refraction is the bending of wave as it moves from a media, from one media to the other of different optical density. Like if a wave is moving from water to air, those two medium will be having optical density. Then you'll have refraction. Now, what is diffraction? Diffraction now is the ability of a wave to spread out So these two, they have produced a secondary wavelet. And this
Mr. Musala? Mr. Musala?
Right.
Mr. Musala,
Hello?
your screen sharing is off. Can you just switch it back on, please?
Okay, should I share the screen again?
Yes, please. It's switched off.
Okay. Is it on?
Okay. Thank you.
All right, thank you. So diffraction will be a phenomenon that will be demonstrating the wave nature of light. So that's what you need to remember. Okay, what we need to do is that last week we did this exercise. So we're not going to be doing this one, rather, we're going to be doing the second exercise, which is this one. So if I can give you 5 more minutes to do this one, and then we'll discuss it together. So it will means it's now 11:22. We'll discuss it at 11:27 or 28, let's say. Right, those who are joining us, we are trying to do this exercise that is projected. So please attempt it so that we can discuss the solutions.
Mr. Musala,
Hello?
one of the learners are asking if you can please go back to the slide about the 2D and the 3D wavefronts. It seems that your connection was lost there and nobody could see you. If you can maybe just explain that one again for them.
Okay.
Thank you.
All right. I'm sorry about that. 2D and 3D wavefronts. We are saying that the wave is so it's an imaginary line that is on the wave and that it is source of wave that moves forward with the same speed as the wave. Now, we're talking about refraction. Refraction is the bending of light rays from one medium to the other. In light from water to the two water are different characteristics. So the light will get light. So because they have those two media, one fraction is the ability as it passes through a around a sharp edge, or as it moves through a small opening. Now the degree of fraction will be directly proportional to the wave, and inversely proportional to the slit width, which is W. So where lambda is the wavelength, as you know it, and then W is the slit width. So do not confuse the two. W is the slit width, and then lambda is the wavelength. Right. Kumela, instead of raising your hand, may you please text your question, inbox me, Melanie will read it for me. All right, we have also said that if you are having, this is the slit width, you are having a wave with a specific wavelength. So if you look here, we are saying, what is a wavefront? Wavefront is an imaginary line that is joining points that are in phase. So these 2 points are in phase. So now it means a wavefront will be here. It will be an imaginary line that will be joining these two, and we'll be having a wavefront here, which will be an imaginary line that will be joining those two. So, but here, what is diffraction? Diffraction is a spreading out of light into secondary wavelengths. So you can see that in here, this one, light is spreading into secondary wavelength. This was the main wave. Now, as it was moving here through the small opening, it starts to spread out into secondary wavelengths. Right. You need to try this exercise, but we have tried this one last week, so the solutions are already here. So what I want you to do is to look at Melanie?
Musala, can you hear me?
Yes.
Okay, just turn on your screen sharing again. It's off again on my side. I don't know if you are maybe experiencing some connection issues, but we keep losing you.
Yeah, I can see. Because the signal seems to be affected by the weather, I'm not sure. Okay, is it back again?
Yes, you're back on again.
Okay, sorry about that. And is shown on the screen. So basically it's similar to what I draw. The only difference is that this one is drawn as dark light. So now, what is diffraction? So diffraction is the ability of waves to spread out in waveforms as small is going is passing through a small or around a sharp edge. And experiment was all about investigating the effect of wavelength on the degree of diffraction. So the criteria for writing the investigative question is so the degree of diffraction is why? Because it depends on the wavelength. So if you increase the wavelength, remember the degree of diffraction will increase. And then if you decrease it, it will also decrease. So from that relationship that we draw. So now we can say that the investigative question, I've said that it must have both variables, the independent and dependent variables. So in this instance, we can say that what is the effect? The investigative question can be phrased like this. What is the effect of wavelength on the degree of the diffraction? And it must have a question mark. And then the other one might phrase it this way. How does the change in wave length affect the degree of diffraction? So anything that shows the relationship between those two will be credited, but it must be in a question form. And now, the other question is that the degree of refraction is recorded for different colors of monochromatic light, and the results are shown on the graph below. On the left, on the y-axis is the degree of diffraction, and on the y-axis, on the x-axis is the wavelength. Now it is write down the mathematical relationship between wavelength and degree of diffraction. So the wavelength is directly proportional to the degree of the diffraction. So which light, red or green, has highest degree of diffraction? So which one between red and green has the highest wavelength? It will be red, obviously. So red will be having highest degree of diffraction. Remember, the diffraction is directly proportional to the wavelength. So here the light with highest wavelength is red light. Right, let's carry on. Right, we have looked at the, these were the responses that have been given. It's only that now they are being written here. We have said diffraction is the ability of the wave to spread out in wave fronts as the wave passes through a small aperture or a round sharp edge. And then the investigative question will be, what is the relationship between the wavelength of light and the degree of refraction? Or how does the change in wavelength affect the degree of diffraction? And number three, what is the relationship between diffraction and the wavelength? The degree of diffraction is directly proportional to the wavelength. And which light will have highest diffraction? Is it red or green? The answer is red. Right. Today, I'm going to introduce ideal gases and thermal properties. That is, I'll be just looking at the motion of particles. That is the kinetic theory of gases. And then we'll continue from there tomorrow. So at the end of this lesson, you should be able to understand the kinetic theory of gases or kinetic molecular theory, and then describe the motion of individual gas molecule, and then describe an ideal gas, and then explain that an ideal gas will deviate from the real gas will deviate from the ideal gas behavior at higher pressure and lower temperatures. And then state the conditions under which real gas approaches ideal behavior. Right. So let's just look at this one. remember that from the kinetic molecular theory of gases, we are saying gas molecules are always in constant motion and they collide with each other and the walls of the container. So what you need to know is that about the motion of individual gas molecules, that they are always in constant motion and they collide with each other and the walls of the container. Because they are in constant they are in state of constant motion, they will be able to collide with each other in the walls of the container. And then there are forces of attraction between the molecules. And then the other thing is that molecules in a gas move at different speed. So because they are moving at different speed, it means they will have different kinetic energy. Remember, kinetic energy is half mv squared. It is half the mass multiplied by the square of the velocity. So they are moving at the different speeds. So temperature will be simply a measure of average kinetic energy of molecules. When you are measuring temperature of a substance, you are just measuring the average kinetic energy of particles of that substance. And then an ideal gas will be the gas that has identical particles of zero volume. The particles of ideal gas, the first thing is that they are identical and then they occupy no volume. They've got zero volume. And then the particles of an ideal gas, they have no intermolecular forces. There are no intermolecular forces between the particles. And then the third point it is that in all collision of molecules with themselves or with the walls of the container, the collision is perfectly elastic. So all the collisions between the molecules themselves and the walls of the container, they are perfectly elastic. So what is perfectly elastic? It means a collision in which there is no loss of kinetic energy. It means kinetic energy is conserved in those collisions. Now, we are saying real gases will deviate from the behavior of ideal gas at higher pressure and low temperature. So if you look here at higher pressure, the real gas will have higher volume compared to ideal gas. They would occupy a specific volume. A real gas at higher temperature, they can be compressed further. That is, at higher pressure, they can be compressed further. So they can occupy a specific volume. They can occupy a specific volume. They deviate from the ideal gas. Remember, something that is ideal is something that is not there, that you wish it could be existing. So real gas has volume at higher pressure. They can be compressed further and they overcome intermolecular forces. Right. So it means higher temperature, you will have higher average kinetic molecules of particles. So now at higher temperature, you might find that this particular gases will be having a particular volume. They can be compressed. But if we come at a lower pressure, you can see that these gases are, the two graphs are intertwined. So it means the real gases and the ideal gases at lower pressure, they would behave similarly. So it means the real gases will occupy no volume. So pressure is the measure of a collision between the molecules and also between the molecules and the side of the container. Right, so we are coming to the end of today's session. So that was just an introduction of ideal gases. So you have to remember the calculations and also the definitions that we have discussed in the last in this session and also in the last session. And also you must continue to use previous DBE question paper just to check your understanding and continue to practice. And when you are having a problem, please don't hesitate to ask question or to ask for assistance. And then you can also use the following link for further information about the lesson. And then I hope that we have gained something from this session. Although there were technical connectivity problems, I think tomorrow we'll be able to go smoothly without any problem. Let's meet tomorrow. We'll be continuing with ideal gas laws. And then I hope that, as I've said, we won't be having any challenge of connectivity. So you can get me or email me at musala.liburu. Sorry, you can email me on this email, musala.liburu@gmail.com, or follow me on Twitter is @musaladl, or Instagram is post_silicon. This brings us to the end of this lesson. Let's meet tomorrow for the lesson will be all about ideal gases law. Thank you.